So it's already 7:05. That is like we are already late by 5 minutes. So we'll start recording the sessions, and those who want to join can join in between. So yeah, this is a course on welding of advanced high strength steel for automotive applications. So we have already completed 1 week in this course, and with the live sessions, and after that the content for second week was released, and now today is a live session for the second week. So the date is 2nd of September 2022. So before proceeding, let me share the screen first, and then we'll start. So I hope my screen is visible. My entire shared screen is visible. So yeah, once again, good evening all. So yeah, so let's start. So in the second week, like at the end of first week itself, we introduced a term called incomplete reaction phenomena. So incomplete reaction phenomena. So here we what we said is that austenite to magnetic reaction which occurs during the tip steel heat treatment. So that reaction is basically an incomplete reaction. So, and we named it as an incomplete reaction phenomena. So before explaining this, we'll just see what was the thermal cycle for austenite for the formation of strip steel. So what we do is, first of all, we'll heat our sample to the intercritical region. So let's say this is our carbon like low carbon region of iron carbon phase diagram, that is the eutectoid section, and this is our intercritical region, that is two phase region. So the phases here are nothing but ferrite plus austenite. So what we will do, we'll heat our sample, and the carbon content in strip steel, as you know, is around 0.15 to 0.2% maximum. So we'll heat it to intercritical region. So what will happen? By doing so, ferrite and austenite will be forming. Initially it is ferrite, which was pro-eutectoid ferrite plus pearlite. Now this pearlite will be transforming above this temperature completely to the austenite. So this will heat, when we heat it to intercritical region, the austenite carbon content will be getting increased. So as you can see, the bulk carbon concentration is 0.15, but when you heat it, the carbon concentration is austenite is given by this line. So it will be more than 0.15. Similarly, the carbon concentration is in ferrite will be very less. So by doing so, what we are doing is we are enriching the austenite by the carbon. So at the intercritical region, will be forming 50% ferrite and 50% austenite. So after that, and this austenite is having very high carbon content compared to the bulk carbon concentration. So now we will be cooling it to a temperature between bayonet start temperature, which we can denote it as BS, and the temperature will be in between martensitic start. So between bayonetic start and martensitic start temperature region, we will be heating it. So by doing so, what will be happening? Hello, can you please unmute yourself? Hello, Rajesh. Hello. Kindly unmute yourself. If you don't want to ask anything, kindly unmute yourself. So what we'll be doing is from the intercritical region, will be cooling it very rapidly, so that our cooling will be in between the bainitic and martensitic region, so that we only transform austenite to bainite rather than transforming to martensite. Rajesh, can you please unmute yourself? So yeah, so what we'll be doing is we'll be cooling it to a region so that we can transform this austenite to bainite. And that bainite is nothing but carbon rich, carbon supersaturated bainite, plus that retained austenite will always be there. And as you can see, the MS line, as we increase the carbon content, MS line is also going down. So the martensitic start temperature will also be getting delayed. So we will be only forming the bainite. But during the formation of bainite, the carbon is getting diffused into the austenite itself. So this retained austenite, whatever is there, is getting enriched in the carbon. But a moment will come when the carbon in the austenite will reach to a critical value, and this critical value is denoted by C T naught. So after that, the reaction between which allows austenite to bainite transformation, it will get stalled. So that reaction will be stopped. So whatever we have so far, that is ferrite plus bainite plus retained austenite, only this much will be left with, because this after this temperature, that is T naught temperature, and in thermodynamic terms we call it as a allotropic phase boundary. So after this temperature, if you are cooling it, then the reaction will be not completed, and that reaction will be named as incomplete reaction phenomena. So basically the diffusion is getting stopped at below the T naught temperature. Up to T naught, if you are cooling, then diffusion is allowed. And if you want further transformation, then only one way that you can proceed is with the diffusionless transformation. But diffusionless transformation is also not possible because the martensitic transformation, which is a diffusionless transformation, for that transformation to start, the MS temperature has very low. So if you want to convert remaining austenite, that is retained austenite, into martensite, then you have to cool it to a very low temperature. Then only the remaining austenite will be converting into martensite. So one more thing is happening at the allotropic phase boundary is that the temperature is T naught, and the carbon concentration in ferrite and the other phase, ferrite is nothing but here bainite. So we can say it as a alpha bainite, and the carbon concentration is austenite. So here we don't have any beta phase. So carbon concentration is bainite and in austenite becomes equal. So these are the two free energy curves of bainite and austenite. So you can see these two curves are intersecting at this point, and this point corresponds to the temperature at T naught. So at this temperature, the carbon content in bainite will be equal to the carbon content in ferrite and carbon content in austenite, and that composition will be in the equilibrium. So free energy at this temperature will be equal for bainite and austenite. So equal free energy at the allotropic phase boundary will be there. So this was all about the allotropic phase boundary or incomplete reaction phenomena. So this austenitic to bainitic transformation in strip steel is also called incomplete reaction phenomena. Now we completed this strip steel metallurgy, and now then we learned about the hot stamping steel. Hot stamping steel. So in the hot stamping steel, what we do, we start with the normal low carbon steel microstructure, which is nothing but ferrite plus perlite. So then we will heat it to complete austenization temperature. that is above the upper critical temperature in the iron carbon phase diagram. So we heat it to complete austenitization temperature so that the complete austenite is formed. And then what we do is, since austenite is a high temperature phase, so temperature is also high. At that temperature, as we know that when you heat a material, so what will happen to Young's modulus and yield stress? So as you heat your material, your Young's modulus and your yield stress will decrease. So you have to apply a very lower load. Let's say you are at the 800 degrees Celsius in one case, and in another case you are at the 50 degrees Celsius. So here you can see at 50 degrees Celsius you have to apply 200 GPa. Young's modulus will be 200 GPa, and your yield stress will be around this like 700 megapascal. So to yield your material at this temperature, that is 50 or 100 degrees Celsius, you need this much amount of stress to apply. But if you are heating your material, let's say you are heating it to 800 degrees Celsius. So in that case, what will happen? Your yield stress will be very low, around 100 megapascal. So at higher temperature, which is in the austenitic region, it will be very easy for you to deform your material. So you heat your material from ferrite perlite to a complete austenitic region, and then after that you do the forming operation. So it will be very easy to form. But while forming, and then you cool your sample so that you form complete martensite. So last week we also studied that in hot stamping steel we add a special alloying element, that is boron, and that too in a very small quantity, that is 30 to 40 ppm. So what this boron does is, this boron effect we'll see in the next slide, but due to this boron addition, the critical cooling rate to form martensite is decreased. So at a even very slow slow cooling rate you are applying, then also martensite will be formed. So here you can see we have a part of CCT, or you can say CCT diagram, where this is our banetic nose. So we are not at all going to form bainite, and rather than we are forming direct martensite. So we are avoiding this banetic region and we are completely forming martensite. So in case of hot stamping steel, if you want to summarize, in hot stamping steel we start with the ferritic plus perlitic structure, but after the formation, after all this heat treatment cycle, we end up with a martensitic microstructure. So at a high temperature you get the advantage of good formability, and at the lower temperature you are getting a martensite which is a very high strength and very high hardness phases. So this, that's how you can play with the heat treatment cycle to get a good combination of ductility as well as strength. So this we already saw in our last class, that by adding boron, so this diagram is with the addition of boron into your composition. So just slightly adding boron, you can see here 0.003% only, 8%. Addition of boron is causing this cooling rate. Initially this cooling rate was forming ferrite, and then here it is forming bainite, but here it is directly forming martensite. So by the addition of very small amount of boron itself, allowing you to form martensite, and this is what we will be taking as an advantage by adding the boron in our composition. So this was all about the hot stamping steel. So if any of you have any doubt, you can ask in trip steel or hot stamping steel. Otherwise we can move to the welding processes used in automotive industries. Adnan Muhammad, and then Tiru Chit Rambalamji. If you have any doubt, you please ask.
Oh, it's okay.
Yeah.
I have already seen the videos,
Yeah.
taking down notes.
Yeah, sure.
I'm waiting for the quiz answers. I have
Yeah.
done myself. I want
Okay.
to cross check.
Fine.
Okay.
Fine.
Okay. Thank you.
So, while explaining, if you feel any doubt or any thing, if you want me to explain, just stop me there, sir. We'll be discussing. So, don't hesitate in that. Yeah. So, we'll move further. So, coming to the welding process that we use in automotive industry. So, as we know that our aim is to minimize the weight and maximize the strength, so that by minimizing weight, the fuel consumption, CO2 emission is low, and by maximizing the strength, we got the crash resistance. So, if we get an accident, then it should be able to sustain that impact, sudden impact. So, for that we are aiming to get a high strength in a very thin sheet of a car body. So for that, the suitable welding processes that we mostly use is the first one is laser welding process, laser welding, and the second one is resistance spot welding. So in laser welding, we have a laser source and then laser beam will be coming, and the welding can be done in two modes, conduction mode and keyhole mode, and all these things we'll be discussing in detail in the week 3 about the laser welding. So this week we'll be mainly discussing about the resistance spot welding. So this is how a resistance spot welding configuration looks like. So here we'll be having an electrode, so mostly made up of copper, that is an high conducting material, and here we will be circulating water to cool the electrode, and the sample which we want to weld will be in the lab configuration, like one above the another. So this is our sample 1, this is our sample 2, both are in the lab configuration, and but below this second material similar to that, this electrode, same thing will be there at the bottom. So here this is nothing but our welded region. So after welding you will be getting a welded region like this. So yeah, so coming to the principle behind this welding, we'll be discussing now. So if you come to the principle behind the welding, so in this image you can see there are many markings here. So these are nothing but to let you know about the resistance at different levels. So the number which is indicated by 1 is nothing but a pure copper. So let's say the resistance is denoted by R1. Here at the interface between electrode and the sample, that above sample is nothing but R2, and the third resistance is the resistance of material itself, and the fourth resistance is resistance between the fairing interfaces. Fairing interface is nothing but where you are going to generate the weld. So this location 4 is R4, and below this also similar thing, R1, R2, R3, R4 will be there. So mainly these 4 types of resistance are there. So if you talk about the total resistance, it is nothing but R1 plus R2 plus R3 plus R4. But out of all these 4 resistances, R1 is coming from the copper, and we know that copper resistance is very much like it's a very good conductor, so resistance will be low. Similarly, this interface will be having resistance, but out of all these 4 resistance, that R4, which is nothing but the resistance, contact resistance between the fairing interfaces. So R4 is nothing but contact resistance between fairing interfaces. Sorry for my bad handwriting, but you can understand. So this R4 is the maximum. Out of these 4, R4 is the maximum. So if you sum up this, so R is nearly equal to R4 only. These 3 magnitude will be very low compared to the R4. So main governing resistance is the contact resistance between the fairing interface only. So that will be helping to weld. So the principle behind this resistance spot welding is nothing but Joule heating. So the main principle is Joule heating. in the resistance spot welding. So Joule heating is nothing but to generate a Q amount of energy, we have I square RT. So this much using current, resistance and time, you can generate this much amount of energy. So this is the principle behind resistance spot welding. So now the same cross-sectional image I have taken here to show you the resistance and temperature, how the temperature varies across the interface and resistance varies. So at this since this is a pure copper, so resistance will be very low. So the moment you encounter the interface here, the resistance will be increased a little bit. So this is the resistance 2, which is between the electrode and the base plate, and then the third resistance is the resistance of your base plate itself, which will be very less compared to the last one, which is nothing but the resistance between the fairing interfaces. So this resistance is the highest one. So you can see the value of this resistance compared to the pure copper or the resistance at this interface. So this is how the resistance will be varying, and due to this resistance the energy will be generated I square RT, and accordingly the temperature of your sample will be rising, and then this is how the temperature will be varying. So temperature at this interface will be maximum, and then here it will be medium, and then here it will be very low, because this is water circulated. So we are circulating water here, so it will be cold only. So the temperature will be very low. Now coming to the weld cycle. So in the resistance spot welding, we use electrode to apply the load, right, as well as to pass the current. So there are basically two functions. So we are supplying current through this electrode, as well as we are applying load P through this electrode. So the cycle of resistance spot welding will be looking like this. So first of all, we apply this graph is for load or force, you can say, and this is for current. So first you apply load, and once certain load is reached, the critical load is reached, then you start applying current, and for a very short duration. You can see here it is only 230 milliseconds. So we are applying current for a very short period, that is in milliseconds, and then after application of current, you just release the load after some time. So what happens is, when you apply load, then there are two surfaces, right? So these two are surfaces which we want to weld. So when you apply load, then the gap between these two surfaces is getting reduced. So when the load increases, the gap, let's say the gap is X, that is getting increased. So due to that, the resistance between these two interfaces will also decrease, because the air gap is now getting reduced, so the resistance will be getting reduced. So this is the advantage of applying load in terms of resistance. So in other way, if you want to show the thermal cycle, so this is how we apply the current and load. So we first apply the load, and after a certain load reached, then we apply a welding current, and then we hold it for some time, we let it solidify the molten metal, and then we'll release the load, and then next cycle from this onwards will start. So this is a very simple cycle that we can see to understand the concept, but in general, in the practical case, the cycle is not so simple. It has many steps, so that those steps will be decided based on the material which you are using, thickness which you have chosen, and the property that you want to achieve. So all these factors will be governing your weld cycle. So here you can see, first of all, we are applying a load, certain load, and after certain time, that load application time is called squeeze time. And after certain time, we apply preheat time. So for that time period, we are applying a very short current pulse with a very slow magnitude of current, and after that we slowly increasing the current amplitude, and then we give a cooling time, then we heat it for certain time with a higher current, and then we give the cooling time. So this is nothing but upsloping, then maintaining a constant current, and then downsloping, and then after that we quench it, that is we let the weld to cool, and once it got cooled, after that also we can apply again a short pulse of very low magnitude current for tempering purpose. So there are three, like 2-3 main things new here compared to this diagram that we will be learning. So the first important thing here is the preheat time. Preheating. So the main purpose of preheating is to minimize the or to reduce the temperature gradient. So what will happen? The temperature difference. So let's say in one case you are welding without heating your substrate. That is, in one case your preheating temperature is 0. That is, or you are welding it at room temperature. So since you know that when you are welding it, the temperature goes in thousands. So from room temperature to some thousand, let's say 10,000 degrees Celsius, or some like very high temperature in thousand you can say. So that temperature difference, and in second case, if you are heating your sample to a certain temperature, let's say 150 degrees Celsius or 200 degrees Celsius. So in second case, what will happen? This delta T, the temperature difference between the room temperature or the ambient condition to the welding temperature will be reduced. So this temperature reduction will be helpful in your cooling rate. So by preheating, basically we are reducing the cooling rate. So that we don't get a brittle microstructure. So like martensite, it's if you are cooling it very fast, so it will be very, very brittle. So to avoid that, you can use preheating to reduce the cooling rate. The second important thing here is you can see the tempering. So tempering. So suppose if you are forming a martensite, so in order to improve the strength or toughness, that is ductility plus strength, so you have to temper it. That is, you have to again, after welding cycle, you have to heat it so that martensite can transform into tempered martensite plus some carbides. So this will basically improve your toughness, that is ductility plus strength. So that's the purpose of these two main things. Other thing is this upsloping and maintaining constant current, and then downsloping. These all are to control the cooling rate and heating rate, so that you won't give a sudden shock to your material. So this is how the welding cycle looks like. So coming to the temperature variation with time, you see here we are completely melting. So this black region is in liquid state, and once you move towards right or towards up or down, the temperature is decreasing. But if you see the length scale, within 1 mm, let's say this is a 1 mm bar, so within 1 mm bar, this is 1 mm bar, you are coming from the liquid to a complete solid region. So if you see the temperature gradient, it is a very steep temperature gradient. So from the liquid state, molten state, you are coming to the solid state within a very short length. So this will give you a very, very high cooling rate and a very brittle microstructure or a very hard microstructure like martensite. So here it is a cooling cycle. You can see at the center here, the temperature is varying like this, and at the edge here, if it is the edge, if you talk about here or here, then the temperature is slightly lower, but within a short time, that is 1500 milliseconds. It's not even a millisecond, is 1.5 seconds only. Within 1.5 seconds, we are coming from a very high temperature, that is around 2000 Kelvin to the room temperature, or you can say if you extend it, it will be coming to the room temperature. So this is how the temperature gradient will be there in the weld zone and in your base material. So coming to the microstructure in the spot welding, you can see since the temperature gradient, which is nothing but dt upon dx, is very high, So that will give you nothing but a type of structure which will be a columnar. So here you can see columns. This columnar structure is growing like that. Similarly, from upward also the structure will be growing towards this, and from this side also the structure will be growing like this. But what will be the disadvantage here? Since it is solidifying from this end towards the center or center line, the impurities element like sulfur, phosphorus, these all impurities will be getting segregated at the center. Segregation will be there. Segregation of these elements at center line. So this segregation is not at all desirable, because these impurities element will be later on may lead to crack formation. So cracking issue may be arising if you are forming a microstructure like this. So this is how the microstructure develops in this process. So we have a technique, we have a different technique to control the microstructure. So that will be seen. Coming to the electrode used, so we have a different types of electrode nomenclature or designation as per ISO or ISO standards. So you can see type A, type B, type C, type D. So all these dome or end geometry are varied. So among these, mostly like we will be using this B type or E type are commonly used, and inside that there will be a cooling provision so that we can cool it easily to don't let it heat it to a high temperature. So there is a phenomena called expulsion happen, which is not at all desirable. So what happens is here in the weld nugget you are applying load as well as current right through the electrode. So here the metal will be melting, and this once and you are applying current as well. So if you see the relation between current and shear strength, here is the graph between shear strength and current. So after a certain time this shear strength starts dropping. So that's happening because of expulsion of metal. So nothing but the weld nugget diameter, if you are increasing the current more and more, so it will nugget diameter will increase, and it will exceeds the thickness of both the sheets. Let's say this is T and T, so 2T. So the nugget diameter in this side will be more than 2T. So the liquid metal will be expelled out. So which is not at all desirable. So expulsion will happen. So and that expulsion will happen at a certain temperature, and that temperature is called Imax. So that critical temperature is called Imax. So you have to use this current below the Imax only, otherwise this defect will be coming into picture. Similar to that, here it is a relation between shear strength and weld time. So you have to sort out the optimum weld time for a given shear strength. So this graphs tell about that. And here then we learned about the configuration. So this is nothing but like how you do fit-ups in the spot welding process. So you have to maintain a certain distance between two spots, and if you don't maintain, then the issue will be arising, that we will be seeing just after few slides. And then from the edge you have to maintain certain distance, and this is the lab configuration which you can see here. And coming to the design, so here you can see continuously you are welding at one side only, other side there is no weld. So this will lead to like stress concentration at one side, and other side it is totally free. So it will be damaging, or it will fail during the service. So the better design is, instead of continuous one at one side, you can use the staggered one, that too in zigzag configuration. So weld here first, then weld here, then come to here, then weld here, then weld here, then weld here. So that the both sides the forces will be balanced in the actual application. Here we saw about the testing of the spot welded sample. So this is nothing but tensile, simple tensile testing, and here it is cross tensile. And what is this? What is the third one? Can any one of you tell? What is the third configuration? So this is nothing but L shape tensile testing coupon, or you can say shear, L tensile shear test sample. So most commonly in the industries we use either this or this, but making sample of this geometry is more difficult than this one, because you have to make a hole in the sample everywhere, like minimum 4 hole, and then you have to apply load upward and downward as well. But here you can see just this L shape plate or sheet we took, and then we have spot welded, and we will be doing the tensile testing, and the strength of weld will be calculated. So here how we determine whether my weld spot sample is good or not. So there is a term called plug ratio, which is defined as the ratio between the actual weld nugget size. So that this is actual weld nugget size before the testing, and after that you do the testing, either L tensile shear test or cross tensile test, and after that after testing you measure the plug size after failure. So this is plug size after failure. So this is the ratio between plug size after failure to the actual weld nugget size. So here it is a one sample I have shown, where you can see this is a welded region which is almost intact, and the failure has happened in the base material. So for our for a good weld, good spot weld, the ideal plug ratio should be equal to 1, and if it is 0, means the failure is completely across the weld. So 0 means what? This was the weld in the first part, this was the weld in the second part. So completely the failure or crack has happened across the weld, across the interface. So in that case the plug ratio will be 0. And in the first case, which is shown here, so this was the size of plug size after failure, and the actual weld nugget size was also this much. So almost it is equal to 1. So it is a good weld, you can consider. Now as I told earlier that you have to maintain a certain distance between two spots here. So what will happen if you are not giving proper spacing between two nuggets? So the effect called shunting effect will be coming into picture. So in that case what will happen? Since here we have made there is no gap, there is no air gap, we have made a complete weld. Let's say this is weld 1, and this is the new weld which we are going to form, WN. So we have already welded this one, and when you are going to weld a new weld, new spot here, when you are going to form, so what will happen? So current will be passing through this interface, but current will be traveling to a least resistive path, that we know. It will form a path where the least resistance will be there. So here it is resistance between the interface which will be very high, and here it is a complete material, no interface like air gap. So current will also flow from this way to this electrode. So some current will go in this way, and majority of the current will go through the weld 1. So during that process, what will be happening? The current loss will be there. Basically we are losing the current, and indirectly we are heating this, because this will have some resistance and it will be getting heated. So which is basically we are deteriorating the property of this already welded sample, and the current loss will be causing less heat generation at this new weld, and thus less heat will be causing a smaller nugget dia. So you can see this one is bigger and this one is very small. So what is happening? Due to the current loss, the new nugget which will be forming will be smaller than the already formed the earlier welds. So which is not at all desirable. So we have to maintain a certain distance between two spot welds, which is shown here, that is certain distance L, denoted by S. Sorry. So this S has to be maintained, and this S is you can take it from the codes or standards. Now coming to the other effect which may be arising due to the use of current, that is DC current. So we have two types of current, DC current and AC current. So we studied about the phenomena called if you have a two different junction at two different temperature, then it will lead to give an EMF, that is seeback effect. So here reverse of this seeback effect, which is nothing but Peltier effect, is happening. So we have two different junctions. This is made of copper and we are welding the aluminum. So due to that, junction 1 is here, other junction is here, and these two junctions are at different EMFs. So that will be causing a different temperature here, here and here, and this will unnecessarily lead to inhomogeneous heating, which is not at all desirable. That's why instead of using direct current, we will be using an alternate current, so that these junctions are we don't get any cold and hot junction. Rather than even if you are getting, it will be switched after every cycle. So in AC we will be using current like this. So after every cycle we will be switching the current. Let's say this is positive, this is negative, then other cycle it will be positive, it will be negative, like that. So we can avoid the problem of hot and cold junction, and then this Peltier effect will be minimized. That's why we use AC current in most of the cases in resistance spot welding. So if you have any doubts so far, then we can discuss it now. Otherwise we'll move to the questions. So please let me know if you have any doubt. Otherwise we'll go to the question section. Adnan or Tiruchitrambalam ji, if you have any doubt, please you can ask.
No doubt.
Okay.
No doubt, no doubts.
Okay. So we'll solve problems, na? Then so first problem is here. You just read it and then try to answer it. Then we'll discuss it. So first question is, when electrode force in resistance spot welding increase. So this is our configuration, and below and from top we are applying load using an electrode. So this is load, or you can say force. So when you increase the force in resistance spot welding, then what will be happening? So these four options will go, and just let me know. Contact resistance between the fairing interface will decrease, that is here the resistance will decrease, or weld nugget diameter will increase, or heat generation does not significantly change, or bulk resistance of the electrodes increases. So whatever you think is correct, just let me know, and if it is right, good. If it is not right, then also good, we'll discuss. You can unmute and say your answer, or you can type also, no issue. So Adnan told like B, that is weld nugget diameter will increase. Okay. Adnan is saying this. What about sir? What about you, sir? So okay.
Contact resistance between the flaying surface interface.
Will decrease.
No, not that. A is not. I think I agree with B.
Okay. So the right answer for this problem is option A only. Why? Because let's say in one case you have a load P1, and in another case you are applying a higher load. So when you apply a higher load, the air gap, like if you simply put two plates, then there will be air in between, right? No surface is completely smooth. So if you zoom this section, so if you see this surface, some surface roughness will be there in both the surfaces. So surfaces will be looking like this, right? So the surface, if you zoom it, it will be having some irregularities and air gap will be there. So what will happen if you apply certain load and then you increase the load? So these surfaces will try to come closer. So when you apply load, they will be deformed and they will be coming closer. So by doing so, the gap between these two will be minimized, and whatever air gap or gap is there, it will be minimized. So by minimizing the gap, what will be happening? Resistance will be decreasing. So you are now you will be now facing less resistance compared to the earlier case where we have applied the less force. So let's say this is the situation 1, and after applying a higher load, the surface will be better, like smoother compared to the earlier case. So earlier we have a irregularities, very much irregularities. Now due to application of load, these irregularities got minimized, so the resistance got minimized. So the right answer will be the contact resistance between the frame interface will decrease, and if the resistance will be decreasing, so what will be the formula? You rating I square RT. So the total heat generated, if you decrease the R, then Q will also decrease. Then if you decrease the Q, then the nugget size, means you are supplying less heat. In that case, nugget size will be decreasing. So the nugget diameter will not increase, it will decrease. Right? So by decreasing the resistance, you are decreasing the heat supply, and then the nugget dia is also decreasing. So this is how we have to solve it. Have you got it? Both of you?
Yes, sir.
Yeah.
Okay.
Yeah. So basically this gap we are minimizing by applying the load. So resistance is getting minimized. So heat supply is minimized, and then diameter will decrease. Coming to the question number 2, just quickly read. In the full interface failure of resistance spot welding, plug ratio is, means we were having a weld here, and after the tension test, the weld itself got failed. So some part of weld went to this sample and some part of weld went to this. So interface failure means failure across the weld. So in that case, what will be the plug ratio? So just now I told in the plug ratio formula, if your weld itself is completely forming, then the plug ratio will be 0. Means your purpose is lost, your weld itself got failed. So in that case, there is no, the ratio will be 0. In the formula itself, you see plug size after weld and actual weld nugget size. So whatever nugget size is formed after this cross tension test or L tensile test, the plug size, the weld itself got broke, then the plug size becomes 0, then the plug ratio will become 0. So the in case of full interface failure, the plug ratio is 0. And in case if the weld is intact, means there is no failure in the weld, but there is failure across the base material, like your material itself got failed. In that case, plug ratio will be 1. Means your weld is intact and the failure is happening through the material. So in that case, weld nugget will be 1. And if it is in between, then it will be between 0 to plug ratio between 0 to 1. 1 is the ideal one, 0 is not at all desirable. So it can vary between 0 to 1. So I hope it is clear. We'll move to next question. Question number 3. Post pulsing in resistance spot welding is generally carried out for. So I told you about the preheating pulse, and then the second one was tempering pulse. It is also called post pulsing. So the purpose of preheating pulse was to reduce the cooling rate. So here in this problem it is asking the tempering pulse or post pulsing. What is the purpose of post pulsing? Okay, tempering the microstructure. So yeah, it is very much obvious. I mentioned in the name itself. So after weld cycle is complete, you can see in this weld cycle diagram here, we are applying this post. After the main pulse is over, we are applying a short deviation pulse with a very low current. So this current is helping your microstructure to get tempered. So the purpose is tempering the microstructure. So you got it right? So the right answer is option A. And what about these three options? Any options which is correct out of these three? Or all three are wrong? Just go through it. Does this post pulsing will cause homogenization of segregated alloy elements, or increasing cooling rate, or increasing weld nugget diameter? So it's kind of post weld heat treatment only. So after welding you are giving a heat treatment, that is post weld. So one of the other purpose of this post pulsing is to also homogenize the segregated alloying element. So as I told you, in that weld nugget dia, this columnar grains will be growing from bottom and from top also, like that. But at the center line here, impurities will be getting segregated, right? So after welding, if you want to minimize the segregation here and homogenize your microstructure, then you can use this post pulsing. So the other purpose of post pulsing is for homogenization of segregated alloys, because now you are heating it and allowing your impurities element, let's say sulfur, phosphorus, to get diffused and move into the other places. So homogenization will also be happening. Increasing the cooling rate, no, this is not the purpose, because cooling rate is already governed by this preheating. This preheating will reduce the cooling rate. Increasing the weld nugget diameter, nugget diameter will not be affected, because for that you need a very high current to alter the nugget diameter. So I hope it is clear. Now you can come to question number 4. The main heat generation mechanism in resistance spot welding is plasma generation, metal vapor interaction, joule heating, and friction. So what is the principle behind heat generation? Heat generation. In the question it is asking principle behind heat generation. So heat is nothing but Q is equal to Vi or I square RT. So this is nothing but Joule's law. Joule's law. So the main principle in this resistance spot welding is joule heating, not the friction or metal vapor or plasma. So the principle involved in the spot welding is joule heating. So we are using current, resistance between the interfaces, we are supplying some time, and as well as we are applying load. So all this current, resistance, time and load are getting utilized to generate the heat and causing the weld nugget formation. So I hope it is clear. Friction is not correct. Have you got it, sir? Friction will not.
Yes.
Yeah.
Yes.
Joule heating you have to mark. Coming to the fifth problem, you can see here on the screen. During resistance spot welding, heat generation is primarily determined by which is the governing factor for determining the resistance, determining the heat generation. Just take it off and then tell you answer. Okay, so absolutely right. The right answer is option D, contact resistance at the paying interface. So the main resistance is that R4 that I told you while explaining the different types of resistance. So the total resistance, if you talk about, it is sum of R1, R2, R3 and R4. And out of this, R4 is the highest one, and you can almost say the effective R is nothing but R4, and that R4 is nothing but contact resistance at the fairing interface. So during resistance spot welding, heat generation is mainly gone by the resistance between the fairing interface. Good. We'll solve the question number 6. In resistance spot welding, Imax is, what is Imax? Maximum current at which steel melts, maximum current at which melt splashing occurs, maximum current at which steel vaporizes, or none of the above. Okay. What about Adnan? What do you think? Just tell whatever you think. If you don't know, then also it's fine. We have to explain it. So Thiru has marked option B. Yeah, no. Please go ahead.
Yeah, I'll also go with option B only.
So the IMAX, when I was explaining the splashing using this curve, you can go back, this expulsion or splashing. So this is nothing but IMAX. So before, if you apply more current than IMAX, so then the molten metal will be coming out of your sample, and which is not at all good considering the shear strength, because this after this the temperature is, this strength is going down. So up to here it is fine, that is Imax, and above that it is not at all recommended. So then coming to next question. Sorry, not at all. What happened to this question? After this I could keep 2 more questions, but it is not at all coming here. I don't know what happened. Okay, fine. There are also some issues came. Sorry for that. No.
In the quiz question posted in the portal, no, I have one doubt regarding one question.
Yes, sir, please go ahead.
For example, this question, when the ultimate tensile strength of the steel increases, failure of resistance part welds, 4 choices are given.
Okay, so is it the assignment 2 you are asking or assignment 1?
This is assignment 2 I am asking.
So assignment 2, like what is the deadline to submit that assignment?
No, this is 7th.
So that answer I cannot tell you. That I have to. We have to wait till 7th. If I will reveal the answer, then it's not good.
No, this I think this assignment only. This assignment what you are teaching us now is we are supposed to submit by 7th. No?
So like actually what we were instructed is if the deadline is later before the like after the class, then we should not tell the answer. But I will tell you the concept, sir. Just read the question for me. I don't have question right now.
When the ultimate tensile strength of the steel increases, failure of resistance part welds. This is how question starts and 4 choices are given.
Okay. So can you?
I think that the choices are not proper. Something wrong. Other 9 questions I could solve. This particular question. 1, 2, 3, 4, 5, 6th question.
Can you please read the options for me, sir? Hello. Sorry, it got disconnected in between.
I will type. When the ultimate.
Can you see my screen, sir? Can you tell me the question number? I have opened it. Can you just tell the question number?
Question number 6.
Okay. When the ultimate tensile strength of the steel increases, failure of tense part welds changes from
failure of resistance part welds.
Correct. So changes from full plug to interface failure, plug ratio remains the same. Change from interface failure to full plug failure, plug ratio increases. So I will give you the hint. I will not tell you the answer, sir. So I will tell you the hint. Just a minute. This particular. You have to refer this particular slide. When, wherever in the video sir was explaining this, just go and re-listen this particular slide, which relate the strength of the sample and the plug size, full plug to the complete failure. So you will solve it. You will get it right. Yeah.
It is obvious. It is obvious. It is there.
So just go and read it.
So as it increases, it goes from full plug to
complete failure.
Interface failure.
Yeah. So that will go and just read. So yeah. Any other things, sir?
Nothing.
Yeah.
That's it.
I kept 3 more questions, but due to some error, it's not at all appearing here. Sorry for that. Maybe we can solve it in next session. So yeah.
Thank you.
Yeah. So thank you for joining. Then if you don't have any doubt, just go and solve all the problem given the week 2 assignment. And if you have any doubt in week 2 assignment, you can ask me in the next session, or any conceptual doubt, we can discuss it here if you have any. Otherwise, fine. Thank you so much for joining this.
Okay, thank you.
Thank you.
Bye.